Well, good morning, good afternoon, good evening to everyone attending from around the world. It's my great honor and pleasure to be with all of you as we go through what I hope will be a very exciting and engaging presentation. At least I know it's exciting to me because encryption is definitely one of the technologies that serves as my passion. And so with that being said, then again, welcome to our presentation today that is titled The Encryption and Password Hashing Recipe with a little salt sprinkled in for good flavor. It is November 20th, 2020, and let's just jump right into their content. As we do so, of course, questions are open. Feel free to type questions into the question portion of the GoToWebinar control panel. For questions, though, I will circle back at the end of the presentation just to give us some nice continuity, but do not be afraid to ask questions, and we'll do our best to get through the questions near the end. I do expect this presentation to go close to an hour. So with that, though, let's just sit back, enjoy, and relax, and jump right into encryption itself. One of the reasons I wanted to put this presentation together is quite simple. Encryption, cryptography, related concepts, they're very, very important. And I don't think that's anything new when I mention that and I say important from a cybersecurity perspective. But what is important to note, and what is still surprising today, is that while it's not a new concept to say that encryption is important for what we do, it's still heavily misunderstood. Where for decades, we've been leveraging some of these capabilities, and it really takes on two areas that become concerning to me from a lack of understanding perspective. The first one is exactly what all of the goals that can actually be met through the use of cryptography, meaning that we don't always take advantage of all the different features available to us. And then secondly, those who usually deploy the controls may not be very well versed in cryptographic concepts at all. And I think that's where I really wanted to start this presentation and where it became the basis for me to build this presentation. Because as it says here, cryptography is easily one of the most misunderstood concepts, and yet it's so important. And if we misunderstand an important concept, there's no way that we can either A, deploy it appropriately, and B, leads to a massive, perhaps security weakness, a false sense of security confidence that comes from the misapplication. When it comes to cryptography, from the use case perspective, it's pretty much, well, open-ended. And yet again, I think we become fixated on specific aspects of cryptography, where the big one that we always hear the most on is the idea of encryption. And when we hear the word encryption, people think of the idea of securing our data, making it unreadable to someone who had unauthorized access. But far above and beyond are so many other goals that could be met, such as things as digital signatures, digital code signing, and even some of the strongest forms of authentication are met by cryptographic needs. And yet, perhaps they're not understood, not applied, or combined together, leading to, again, that kind of massive weakness. Perhaps, though, going along that theme of the misunderstood aspect, I'll get right to it right now. Cryptography is not synonymous with encryption. And yet those words are used interchangeably in the sense that it's almost one for the other. When people talk about cryptography, they often hear the word encryption or they mean encryption. And yet encryption is but only one aspect that could be met through the use of a cryptographic system, a method that could provide a security concept. Cryptography is the study of the science and the techniques that allow for communication to occur in the presence of a third party in a more secure manner. So again, to summarize that differently, the practice of secure communication in the presence of a known adversary. It's cryptographic systems that allow for many goals to be met, of but which one is encryption. And again, that goes into that misunderstanding, where if we only focus on encryption, not only are we missing everything else that could be done, but we probably won't even understand the encryption aspect itself, still because of that misunderstanding. There are 4 common goals that can be met with the use of cryptographic systems. And the first one, of course, the one that's always thought of again, the idea of providing for confidentiality through the use of encryption, where we can take an object and go from its unprotected form known as plain text. We apply perhaps a mathematical algorithm in combination with a digital key to lock and create encrypted ciphertext. Or I should just say ciphertext, because that's anything in its protected form. Ciphertext through the process of decryption, applying a mathematical algorithm in combination with a digital key, will yield back a corresponding plaintext, the object in its original form. When it comes to the term text, in either plain text or ciphertext, I just want us to be aware that it doesn't have to actually be text. Those are just words we use. But again, it's not just confidentiality that's the most important, or, right, to say it differently, the other ones have their own place, even where sometimes confidentiality is not important at all. What about the idea of integrity? Integrity is the idea of using hashing algorithms to verify and validate that an object has not been modified in any way, shape, or form. Or what about authentication? Authentication is met through the use of asymmetric encryption systems, or at least that's a goal that can be met using a specific cryptographic system. When it comes to authentication, some of the most secure forms of said authentication are because of cryptographic concepts. Things such as public-private key pair cryptography, that's another name for asymmetric, or that's a part, I should say, it's applied to asymmetric understandings. Public-private key pair represents the most secure form of authentication because it's a mathematical relationship which is not easily spoofed. It's very improbable to spoof, all things being equal and relevant, of course. Then last but not least, non-repudiation. Non-repudiation can be a legal concept that can uphold things like a digital signature in a court of law. And that's a combination of hashing and asymmetric encryption cryptographic systems together. Many different goals that can be met, where again, encryption is not synonymous with cryptography. Cryptography encompasses many different goals, of but which encryption or confidentiality is only one aspect. I think what I've also, above and beyond, adds into some potential confusion is that we often use encryption and other aspects of cryptographic systems together for things like authentication. And it's the mix and matching without the background that lead to confusion. Confusion leads to weakness or a lack of application altogether. Some of these concepts may be new for some, may not be new for others. But again, it's so fascinating that these concepts are not new as a general sense. And even still as such, they are misapplied or not used today. If I had to give a big picture of what would be really valuable as a key takeaway for anyone who's attending now or listening to the recording, it would be this particular slide, where this slide shows the big picture of not only the different types of cryptographic systems that we can leverage, but the names of some of the algorithms, some of the ciphers that go into those cryptographic systems. We hear lots of different names, lots of different terminologies and technologies thrown around, especially in the cryptographic space. And yet, well, clearly the names don't all mean the same things. We know that symmetric cryptographic systems, as it's shown here, will have algorithms with names such as DES, triple DES, AES Rangdoll, and so on. Asymmetric cryptographic systems might use algorithms with names like DSA or ECC, RSA. Hashing algorithms, names like MD5, SHA-1, SHA-256. And something we won't discuss here, but could be the subject of another upcoming presentation, will be the idea of how important it is to protect and to manage, therefore, the keys that are leveraged in these cryptographic systems as well. And of course, I did say that's a really important slide. And the next most important slide is actually the one that follows, where it ties everything together up to this point. We now see that the different goals of a cryptographic system are met by different types of cryptographic systems and some of the related names of the algorithms in that system. And this can be a really, again, a highly valuable takeaway as we continue our journey in cybersecurity, or just as a reference point when we're trying to figure out which algorithms go into which category. Our confidentiality is met by the symmetric with names like DES, triple DES, and so on. Integrity goals are met using hashing algorithms, authentication with asymmetric, and non-repudiation is a combination of the two of them together. That's asymmetric and hashing. And it's those combinations, again, that I think sometimes lead to some potentials for confusion. But I get it. You know, if this already sounds confusing, isn't that kind of the problem? So with that, why don't I actually go through some examples here? We'll do a little bit of demonstration to try and highlight and tie these concepts together. Because if there was one last example, just before I get into a demo, to show how potentially confusing some of the concepts can be just from the initial observation perspective, it would be that encryption is not synonymous with hashing. Now, we know that that's the case because, let's take a step back, encryption, the idea of confidentiality, is met with symmetric algorithms. Hashing, the idea of integrity, is met through the use of hashing algorithms. They're two separate concepts. They're used for different goals, but they are often tied together, especially for authentication. And that's where the password recipe with a little bit of salt sprinkled in is going to come into this presentation. These initial slides are just the foundation to make sure that we have a solid understanding of everything that's going to follow next. Encryption obviously is not equal to hashing for all the reasons we just exposed, but let's really dig down into why it's not the same. Encryption is the idea of being reversible. We go from plain text, an object in its original and unprotected form, to ciphertext, the object in its protected form. If an adversary was to observe ciphertext, they cannot make sense of it because it's the encrypted representation of the plain text object. But of course, we ourselves, we do need to be able to access that data again. And so therefore, we would be able to decrypt, and it would be necessary to be able to decrypt that the ciphertext back into the plain text equivalent. Encryption is designed to be reversible, whereas hashing is not. Hashing is irreversible. And clearly, that's a big difference between encryption and a hashing concept. The lack of reversibility. It's not reversible because what happens is a one-way mathematical transformation is performed by a cryptographic system. And it's that one-way mathematical transformation that leads to its value and its use for integrity. Okay, but with that, enough of that. Before we go any further, let's get a demo so we can start to apply these concepts because it will become important. I happen to have an object here in my file system, and it's a file, io.txt. It's clearly a text document, and this document was written to indicate that I owed some money to my best friend. Let's take a look at the document. The document says, I owe my best friend $500. To my friend, this document has a lot of value, doesn't it? This document is essentially worth $500 because it clearly says that I owe my best friend $500. My best friend will want to know if this document ever changed because, well, I could just change it and say, well, no, I never said that. I said I owed you $50. This document has intrinsic value, and my friend would want to ensure that it was never modified. My friend would want to be able to verify that the document has integrity over time. Integrity is met by the use of a hashing algorithm. I could use a very simple algorithm like MD5. And yes, MD5 has problems, but it's okay for the use as an example in a demonstration. I have a tool MD5 deep, and I'm just going to run this tool against that file. That file, io.txt, the binary ones and zeros that represent that file are sent through the mathematics known as MD5. That's the tool does for me. And when the magic and mathematics of MD5 are applied to the file io.txt, we receive this computed value that we see here on screen, alpha 0191 delta delta, and so on. This value is the hash of that file. This hash represents the uniqueness of the binary ones and zeros of that file. It's not the file name. It's not the idea of the location on the file system. It's not the modified date and time of the file. It's the binary ones and zeros that make that file that file. It's like a fingerprint. If I was to try and modify that file, I'll make a very small change for me, a big change to my friend. I owe my best friend 50. Only simply deleted the 0 at the end. And now when we run that hash again, we see that not only is the hash different from the original, it's dramatically different. There is no similarity between the two hash values whatsoever, even though I made a very small change. That's one of the most important considerations that goes into the development of some of these mathematics. My friend could say, well, the integrity has been invalidated. The integrity has been lost. And therefore, my friend could say, hey, Bryan, I don't know what game you're playing here, but that's not the original file. And then I could say, oh, I'm so sorry, I must have made a mistake on the file. Let me just put it back. What was it that I owed you? Oh, 500. My bad. And we put the file back to its original incarnation, we see the hash returns to the original value. It's integrity checking. Now, again, perhaps in some perspectives, for some people, that may not be new, but here's where it gets to be really interesting. That value is not reversible. You can't take that value and go back to the plain text object. And I know it seems unlikely, but again, here's how we get a quicker understanding. That's the whole point of the presentation. This is simply a representation of uniqueness. The uniqueness of the binary ones and zeros that make that file that file. It's just uniqueness. It's not a storage of the content of the file. It's the uniqueness, like a fingerprint. That's what makes it non-reversible, because it's not actually the content. Now, there's a little more to it, but that will be in the presentation. And I simply provide that to keep us going in that perspective, to show that hashing is designed to not be reversible. Encryption, we want to be reversible. Hashing, we don't. Why is this important? Because of its use in authentication. That's where we're going to get to passwords. Passwords are, even still today, one of the most common factors of authentication that's used. If we really wanted to tie it together properly, though, to have a singular view of another aspect of why it's irreversible, we can look at this slide next. Now we have the different types of cryptographic systems and the number of keys, digital keys, that are leveraged in the process. Symmetric cryptographic systems, confidential purposes, we know we take an object that's plain text. We apply a digital key with an algorithm through the process of encryption yields ciphertext, protected form, confidential. Ciphertext decrypted into plain text, leveraging that cryptographic algorithm and the exact same digital key that was used to lock is used to unlock, going back to the plain text. Symmetric is one key cryptography. The key that locks is the key that unlocks. Asymmetric cryptography is two key cryptography. That's right, there's two keys, key 1 and key 2. These keys are created simultaneously by a cryptographic computer. The keys have a mathematical relationship to each other and only each other. And those keys therefore form a key pair, a pair of keys. Key 1 and key 2 is the name we'll use originally. What's really unique about how the keys work is that whatever you do with one key, only the other key can undo. As strange as it sounds. If we encrypt with key 1, only key 2 can decrypt. And if we encrypt with key 2, only key 1 can decrypt. Now, we're not going to go too much into the names, but I do need to change the names so we understand appropriately. Don't let the names confuse you. Just remember that whatever one key does, the other one undoes. Public key, private key. Public-private key pair cryptography. And yes, if you encrypt with the public key, only the private key can decrypt. If you encrypt with the private key, only the public key can decrypt. And as strange as it sounds, yes, there are use cases for that, because that's a way to prove authentication. If you encrypt something with your private key, then it was encrypted by you, and we can verify by using your public key. The public key is private, or the public key is public, pardon me, and therefore anyone can have access to the public key. Knowing that something was done with the private key is kept in secure storage, lends confidence to things like authentication. And then, of course, there's hashing. Well, hashing doesn't involve a key. Some people, that's how they like to remember that hashing is irreversible. There's no key. But that's not exactly the entire aspect, but it is no-key cryptography, right? That's a no-key concept. So one-way mathematical transformation where we go from plain text to a hash value. There's another reason it's irreversible, but we'll get to that in a moment as we move towards passwords. We're getting there. So I have to build this foundation. To summarize then, to show that symmetric cryptographic system, I did want to give a picture because these things can be very abstract otherwise. We have Alice and Bob. Alice and Bob are two of my very good friends. They're often used as the characters in examples of cryptographic communication, or I should say, secure communication in the presence of a known adversary. And for Alice and Bob to communicate for confidentiality, Alice takes the plain text message, she applies a cryptographic algorithm like AES, this is symmetric, with the secret key that will yield the ciphertext. The ciphertext will go across the wire, and even if intercepted by a third party, the communication is not readable because they do not have a copy of the key. Alice and Bob, they have the key. Bob receives the ciphertext, applies the same cryptographic algorithm like AES with the application of the same key. The key that locks is the key that unlocks, to yield back the plain text. There we go, that's confidentiality. Hashing, the summarization slide for us here, the final reason that it's not reversible is there is a reduction. The input that goes to the hashing function is reduced to the output. So let me explain. We saw MD5 in this demonstration. MD5, the output length is 128 bits or 16 bytes. If you have a 100 megabyte plain text file that goes to the hashing algorithm, you end up with 16 bytes of output. If you have a 4 gigabyte file, you end up with a 16 byte hash value. And there would just be no easy way at all to go from 16 bytes to 4 gigabytes of uniqueness. Because once again, a hash is not the storage of the data. It's a storage of the uniqueness of the data. It's a fingerprint. You wonder perhaps why I keep coming back to that very specific notion that a hash is not the storage of the content. Well, here's the reason. The additional uses for hashing. Passwords. Think about the dilemma that we face when it comes to using passwords. The dilemma of how passwords themselves must actually work, and how they work actually becomes its own weakness. So let me explain. Now again, I'm going to go take this slowly. We'll go easily here, as easy as we can be. And to be fair, some of what I'm going to say next is very obvious. And it's okay. You might say, well, thank you for that obvious statement, Captain Obvious. But sometimes we ignore the obvious, and that again leads to weakness. I sit down at a computer system and I type my username and password in to submit it to the computer system itself. If that username and password combination is correct, I'm authenticated and the computer logs me in. Yes, Captain Obvious, that's how it works. Okay, great. If I type my username and password, though this time the password itself is incorrect, I'm not authenticated and I can't log in. Yes, Captain Obvious. It's great. I'm glad we're on the same page. The biggest and most important part of that set of statements, however, is the question of, well, how does that work? If I sit down and I type my password correctly and it logs me in, I type my password incorrectly and it does not log me in, then that must mean, does it not, that the computer has some knowledge of right versus wrong for my password? Yeah, I guess it would, wouldn't it? Because it knows the difference. Otherwise, I could just type whatever I wanted. But when I type it correct, I'm logged in. Incorrect, I'm not logged in. Okay, great. So now we're starting to understand how it works, or how it's intended to work. But that also means then that in some way, shape, or form, all things being equal, a computer system somewhere knows my password. So it knows the difference between right and wrong. The big issue is that computers are not human. They can't remember anything. They know what they know because they read information from storage. So yes, that would have to mean my password is stored somewhere so that as a computer system starts up, it can read my password value in some way, shape, or form, so that when I attempt to authenticate, it can compare it to what I'm supposed to type relative to what I actually typed. Okay, yeah, I guess that makes sense. Right, but if a computer can't remember and it reads from storage, if an adversary was to break into that computer, wouldn't that mean that they could read that value too? We program computers to do things on our behalf, which means that a computer is doing something that a human should be able to do, just faster. And so now, if we extrapolate that further, we have systems for authentication where all of our users have some attribute of their password being stored. And if an adversary broke into that system, they could steal those attributes. And wouldn't that be game over? Oh, right. One of you sent me a telepathic thought. Well, let's store those passwords securely then. Fantastic. Oh, right. And secure storage means encryption. Okay, cool. So encryption is confidentiality. We're going to take the password, use an algorithm, use a key, lock into ciphertext. Awesome. And then this way, if the adversary breaks in, they have ciphertext. They don't actually have my password. Sweet. But wait, hold on. Doesn't the computer still need to know? If it's encrypted, doesn't the computer need to decrypt to compare my password? Right? What I typed to what was stored? Oh, all right. Okay, so no problem, right? I mean, the computer just reads the key. Wait, that's right. The computer can't remember. So the computer is going to read my key, a symmetric key, to decrypt the password. But if the computer can read the key, can't the adversary? Oh, what a dilemma. Oh, I know. Okay, we need to secure the key then. So we're going to encrypt the first key by using a second key. Adversary reads the second key to read the first key to read the password. Don't. It always feels like cat and mouse. It does. Okay, we're going to encrypt the second key with a third key, doing the same thing over and over again, expecting a different result. It truly is the definition of insanity. And right there, we have a dilemma. Passwords are important. They're a factor of authentication. Passwords are still used heavily today, and yet they have to be stored, but we can't store them securely. What a nightmare. Unless we find a better way. And that's where hashing comes in. Hashing was never designed for password storage, but it could be used for password storage. Now that we've had some examples and some demos, let's further that demo. So here's what I mean. My password is the word koala. Why? Because koalas are cute but deadly. They can hurt you, but they're cute animals. So koala is my password. And to be fair, what I'm going to emulate next is just for discussion. It's just for ease of understanding. A computer system will do much more than what I show here, but it helps us to understand enough to the point where we can continue forward. I'm going to emulate what a computer might do. I use the echo command. The password is koala. Echo koala. Say koala. Koala, like an echo. When I take that value and send it into that same tool you saw earlier, MD5 deep, we're going to take the value koala and take an MD5 hash of koala. And there's the hash value. This value is going to be stored on the computer system to represent my password. But what did we already learn? Hashes are irreversible. They're irreversible because it's a one-way mathematical transformation where the input is reduced. This value is not koala. It's not the content koala. It's the value that represents the uniqueness of the word koala itself. That's going to be stored. And already that's much more secure than reversible encryption. Encryption and hashing are not the same. Yes, an adversary could break in and they could steal password hashes, but that's not what you type. What we type is actually the value that went into the mathematics to produce that value. Okay. Now, just to finish the example then, well, how does it work when we log in? This is stored with my account. The next time I log in, I go through the same process. I type koala on the keyboard. Behind the scenes, the computer takes that value, does the same thing as before, and this time is computing a value based on what I typed. The value based upon what I typed is compared to what's stored for my account. If they match, I type the proper password. Only my password will produce that value. You see, now we get an extra benefit. The computer doesn't actually even know my password. It takes what I type, goes to the same mathematics, and compares mathematical results. It doesn't have to know my password because it can't know my password. It's irreversible. If I happen to type it incorrectly, we'll leave out that A. The value we compute does not match what is stored. Therefore, we're not authenticated. An adversary can steal the password hashes, but they don't know the actual password. And it's not reversible either. So now we get some extra benefit. Oh, okay, but to be fair, the next obvious question that would come up would be, well, then how do adversaries crack passwords? Cracking passwords doesn't mean reversal. Cracking passwords means going forward. We don't go in reverse, we go forward. We steal hashes, we supply them to a password cracking program, and then that program will attempt to guess what the password might be. Is the password KOA? Go through the mathematics, compare to what was stolen. The one at the top is the one that was stolen. It doesn't match. Try again. Is it KOAL? That does not match what was stolen. Try again. Is it KOALA? Oh, that matches what was stolen. Congratulations, you've cracked the password. Password cracking, as applied to password hashes, is password guessing. You guess what the password might be and run through the same iterations, the same mathematics. That's what password cracking is. The reason we don't call it password guessing is that the term password guessing is reserved for the attack where an adversary is at a keyboard. Conceptually, they could be doing software with automation, but it's like they're typing a password at a keyboard trying to actively log in. This is just mathematics on things that have been stolen. That's what password cracking is. That shows the value of doing hashing for password storage because we're not storing content. Great. Yeah, that's some pretty cool stuff. Wait, I know questions that are probably in your minds right now. First off, do we know which mathematics are used by which operating systems? Yes. Wait, shouldn't that be a secret? It can't be. First off, that type of secret would never stay secret because the computer itself has to know which math to use when you try to log in. So it's actually not secret, and the computer couldn't keep it secret forever anyway. Secondly, it's not the point. Do we know how the mathematics work? Yes, that's also not a secret. These concepts must be exposed to cryptanalysis for long periods of time. Cryptanalysis tries to show us that what we believe to be secure might be secure. We actually never know for sure. What is secret is the strength of the quality of the password we choose to use. That's the secret. Yes, if an adversary stole our password hashes, it could be problematic because a question could be, well, what if two different people have the same password? Well, they have the same password hash. In this case, yes. That's because there's no salt being added. Here we go. That recipe, the password recipe, we don't have enough flavor. Salt is where we sprinkle some uniqueness into the password itself, into the process, so that two different people with the same password have different password hashes. And again, let me explain a little more clearly. These are really difficult concepts. Here, two different users have the same password and therefore have the same password hash. When an adversary breaks in, the adversary could determine that those two users have the same password because the hash is identical. If they could target one user gives up their password through some sort of social engineering, while the adversary can now log into multiple accounts. Assault is adding uniqueness, and the computer will pick that uniqueness and it's stored with each account as well. So let's say that for the first account, the computer is using a salt value of 1, 2, 3, 4, 5. It's not always added to the end. This is just for demonstration. I type koala. Unbeknownst to me, the computer adds another value, 1, 2, 3, 4, 5. All of that goes through the mathematics, and there's my hash. The second user, who happens to have the same password of koala, goes through the same mathematics, but they have a different salt value. Each account has a unique value. Because the inputs are now different, the outputs are different. An adversary, by simple observation, is unaware that these two users have the same password at the keyboard because the password hash is different. That's where salt comes in to add strength to password hashing. All right, so with all of that demoing then, let's review what we've learned. Passwords are going to be stored leveraging these concepts where we have our clear text password we go through a function called a KDF, a key derivation function, to produce our hashed value. Now again, it's not the actual password, it's a representation of the password. That will be stored with our specific user account. The next time we try to log in, whatever we type goes to the same function. The output is compared to what's stored, and if it matches, we're authenticated. The things that I did in the demonstration, again, were simply for demonstration purposes. We want to go above and beyond that, and we want to use a proper KDF, so not just MD5 the way I showed it, where a KDF has certain functions and certain features. It has to be irreversible. We've explained those concepts. It's going to transform the input into an output where there's no comparison or matching between the two, meaning that knowledge of one does not imply the other. We want to add in uniqueness above and beyond. That's where we can add salt, and even today, pepper. That's right, salt and pepper. Same concept, just different storage. And on top of that, more importantly, above and beyond, even at this point, a difficulty factor. How many computations does the process actually involve? The more computations, the more complex it is for a CPU, the slower the attack becomes for the adversary, all things being considered equal. Let's just say that for arguments and example's sake, if it took 3 seconds to calculate a password hash, that means a user is delayed by 3 seconds on logging in. That might be acceptable and okay. For an adversary, all things equal, that would be 1 guess every 3 seconds, or 20 guesses a minute, or 1,200 guesses per hour. If it was a calculation in 1/10 of 1 second, that's 10 guesses a second, 600 guesses a minute, 36,000 guesses per hour. Cost is very important in these calculations, and that's known as the difficulty factor. Wow, it's hard to believe how in 43 minutes already, we have such a deep level of understanding. It's impressive how quickly we can get up and running. We just sit back and take time to go through it. Because you see, that's exactly what happens in one of the most commonly used functions that we have today in use, PBKDF2. This is the password-based key derivation function version 2. It's the idea that we have a pseudo-random function, maybe like HMAC SHA-256. And so that's the idea of our algorithm. The password, salt, the number of iterations from a cost perspective, and the length of the output. Those are all important aspects that go into PBKDF2. There we go. We now know how passwords work. But why is all of that important? Well, let's circle back. Passwords, even though for 30 years, more than 30 years, I've been hearing how problematic passwords are and that passwords will eventually go away. They haven't gone away. And yet each year that ticks by, passwords become the sole factor of authentication for the majority of accounts across the globe, whether it's in an on-premise, like in your own environment, or in the cloud. Single factor. On top of that, passwords are so difficult for humans because we encourage things like complexity, special character, uppercase, lowercase, number, that people end up using password tricks to bypass complexity because it's hard to remember a complex password. $, $, W0RD, the word password with modifications, might pass a complexity checker. For a human, it actually might be hard to remember. Was the A the @? Were there $2 signs? Was the O an O or a 0? For a human, it's complex. For a computer, that's trivial to break. And yet, still in the year 2020, the amount of accounts that leverage only a single factor is staggering. We're not learning from the past, and so we're being forced to repeat it. And still, you know, in the 2019, yes, last year, the top 10 worst passwords that are still in active use, the word password is in that list. password 123, password 123456, still in the list, even to this day. And how do we know that? Passwords are stolen. Passwords are disclosed to the general public. We know which passwords are being used. Now you compare and consider all of that. And then, well, we could naturally come to a point where people are confused and concerned about what does this mean for cloud? Because, well, as the synopsis for this talk did discuss, we were bringing up an example of cloud. What we've discussed here can be done on-prem and in cloud. But cloud really does change the conversation, does it not? I mean, on the one hand, an adversary breaking into one's environment is one consideration. Breaking into an environment in one's cloud, it automatically feels different by the nature that our cloud capability is external to us. It's on someone else's hardware. So therefore, if we did a natural translation, I guess using cloud is even more insecure, isn't it? Or is it? The question would be, how does our authentication work in the cloud? Different cloud providers, different answers, and I only had enough time as we see to pick one. So we'll pick an example. A very big cloud provider, we'll pick Microsoft Azure. Many organizations, of course, have an on-prem Active Directory for central authentication. And then there are questions as to, well, how will we authenticate to our cloud capability if we're using Microsoft Azure? Do we have separate accounts, cloud accounts and on-prem? Do we have only a single set of accounts that are on-prem? If they're on-prem, how do they authenticate in the cloud perspective? Lots of really important questions come up at the beginning. But just to circle back specifically to what we've discussed, there is the option of synchronizing our passwords from our on-premise environment to the cloud. Single set of accounts, that's ease of use for the users, and now Microsoft Azure Active Directory, that's centralized authentication in Microsoft Cloud. Well, now they have a copy of our password hashes. So this is great. Now we can log in locally and in the cloud, single credentials. Oh, no. Brian, you just showed that password hashes can be stolen and password hashes can be cracked. And the one thing you didn't talk about, Brian, but if people's password hashes are stolen, maybe they could just pass the hash. You just send the hash and that logs you in anyway. You might have heard of those attacks. In other words, just possession of the password hash is a problem. So this is no good. So therefore, synchronizing by passwords to Microsoft Azure AD must be dangerous. And if it was synchronized, it would have to be my plain text password being synchronized, so that could be read by Microsoft. And even if that wasn't the case, obviously I'm looking through maybe some misconceptions here. Or what if it, well, okay, let's assume that Microsoft can't read it, but if my password hashes are synchronized as exactly as they are, then they could be stolen in the cloud and used in my own environment. Well, that's no good. And of course, while maybe cloud is less secure, I mean, these are things people think. These could be potential misconceptions. But maybe we should actually clear up those confusions. So let's talk about that. First off, Azure Active Directory Connect. Always ask that important question going forward for anything you do. How does whatever it is work? For Azure Active Directory Connect, here's what happens. Inside your own environment, your own organization, your hash is transmitted securely internally from things like your Active Directory domain controllers to a specific agent. And it's this agent that will then synchronize with Microsoft Azure Active Directory. So there's an internal exchange of your hash and it's secure across your internal network. So that's good news. Next though, the hash that is in the on-prem environment, the hash you would use to authenticate locally, that is not the hash that is actually submitted to Microsoft for Azure AD. The hash that you have goes through a rehashing process itself, not the plain text password, the actual hash. So you take the hash, there is a salt, and it goes into PBKDF2, the function we discussed. 1,000 iterations of HMAC SHA-256 are used for complexity. And that resultant hash value is then submitted to Azure AD. Translation: the hash you have on-prem is not what's synchronized with Microsoft. A more secure form of your password hash is synchronized to Microsoft. And when I say more secure, because the hash itself was hashed, leveraging strong cryptographic capability, that's what makes it more secure. And after that, it's then sent, it's encrypted for confidentiality. There you go, hashing and confidentiality being used together. It's encrypted over TLS. It's submitted to Microsoft securely across insecure networks. So even if intercepted in transit, it's been protected. What does that mean though? Like all in all, what actually means this: not only is the hash that's submitted more secure than on-prem, the hash, if it was compromisable on Microsoft's side, it actually cannot be used against the on-prem environment. It cannot be used as is, meaning like a pass-the-hash attack, because it's not the same hash. Theoretically speaking, if Azure AD was compromised, your on-prem environment is still secure, assuming you have a strong passphrase, assuming it's not a common passphrase. But what you actually submit is better than what you do on-prem. So to clear up those misconceptions from 2 slides earlier, the hash that's synchronized is not the actual hash, it's rehashed. The hash that's submitted uses strong cryptographic concepts. The plain text value is never disclosed to Microsoft. They can never read inside your password, regardless. And if an adversary did steal it in the cloud, it cannot be used to pivot back into one's on-prem environment. Wow. It's doing it better than on-prem. That's what shocks me so much. You know, we tend to have these concerns about moving to cloud. And don't get me wrong, I'm not saying that cloud is naturally more secure, but what I will say is that cloud itself might represent an opportunity to redo our environments because we build new in the cloud, do it right from the start. And some of the capabilities that major cloud providers provide from a security perspective can actually be done to a higher degree with an easier level of implementation than had we tried to do it on-prem. It's amazing. Cloud is here to stay. And that's one of the other really important takeaways I'd like to have here for you, is that it is here to stay. And that we should be advocating in some way, shape, or form for cloud when our organization says that cloud's important to them. The time is gone where we could be the no people. Once upon a time, we could say no and dictate what and what would not happen from a productivity perspective. But those days are long gone. And we should never have done it to begin with. If we say no, all it means is we will not be involved in those important conversations where we can determine what that authentication will look like in cloud, how we will synchronize or mix and match our capability. And last but not least, even if above and beyond, even if after all this, someone still says, no, we can't synchronize our password hashes to Azure AD Connect specifically, then perhaps it's fear that's driving that decision. And just as a kind suggestion, I would say never let your emotions drive any of your decisions when it comes to information security. Let your data drive your decisions. And even if that, at the end of the day, they were still worried, then this is why multi-factor is important, isn't it? Because if we really wanted to circle back, the whole problem is that we only use a single factor, the password. Multi-factor, multiple factors have to be leveraged. The password logs you in halfway, and then you have to have a second factor, maybe a software token on a phone, whatever the case is that we're doing. Multi-factor is really what we should be doing anyway, on-prem or in cloud, and especially in cloud. So it's those different types of mix and matching that become important. And yes, multi-factor, there are obstacles, specifically ease of use, and then perceived difficulties in implementation. It's actually easier to do than most people would give credit towards. And I think, you know, that's what concerns me the most, even above and beyond all this, is that for MFA and how capable it is, it's just not being used. I'll give some statistics and examples. This actually came from Microsoft themselves. As a cloud provider, they have a great view on what happens to their end users, their subscribers. They see a lot of attacks just based on the infrastructure. They have said in their own studies that an account with multi-factor is 99.9% less likely to be compromised than a single factor of a password alone. That's right, 99.9%. That's amazing. But you want to flip it around? Here's the other statistic that's concerning. For Microsoft, they know that for Azure Active Directory accounts, only 8.2% of those accounts are using multi-factor, even though it's 99.9% less likely to be compromised if you turn it on. Only 8.2%. Okay, you're right. You know what? I'm actually going to do one thing more. If you just pay for another order, just shipping and handling, I'll give you one better here. And here's the one better. When I heard that statistic from Microsoft that 8.2% of Azure AD Connect accounts were using multi-factor, I didn't think only. No, I didn't say only. I thought, are you kidding me? That's amazing. 8.2% of Azure AD accounts are using multi-factor. That's incredible. We should celebrate that. Because when you look at multi-factor in cloud as a whole, across the industry, the uptake rate is estimated to be 0.1%. Only 0.1% of all accounts in cloud perspectives like Google, Amazon, Microsoft, LinkedIn, Twitter, Facebook, only 0.1% of accounts worldwide ever turn that on. And yet it's such a strong protection. So for yourself, I would kindly suggest that for you, where you can turn it on, you should. Hundreds of websites, free apps to generate those one-time passwords for you, protect your account. And of course, you should use a unique password for each website and each property that you log into as well. So with that, then, in ultimate conclusion, let's summarize. Cryptography clearly is not encryption alone. And encryption is not the same as hashing. Synchronizing to a cloud provider like Azure AD Connect actually resulted in a more secure password hash than doing it on-prem. Different cloud providers will have different options. You'll have to seek out those options, but it's always interesting to see how things actually work. For example, Amazon for AWS, they support federation of services, which means that you could actually authenticate to Amazon Cloud by leveraging your Microsoft infrastructure. So you could take advantage of Azure AD Connect and all of its power using federation with a different cloud provider. And at the end of the day, passwordless is the future. A day where it's multi-factor, but passwords is not one of the factors. That day is a long way off. But it's a goal that we need to continue to move towards. And with that, it does bring us to the end of my lecture portion of the conversation. I mean, it's such an interesting topic, and you can see how difficult it is to fit into 1 hour, and I've got 1 minute left. But don't worry, while the lecture might be done, there are questions I'm sure that came in. So let me just go ahead and take a look here to see if there are any questions. Well, I'm actually not seeing any. Oh, actually, maybe there is. Sorry, pardon me. No, I'm not seeing any questions. Carol, are there any questions that you're seeing on your end?
No, I'm not seeing any either.
Okay, well, with that, I hope that everyone enjoyed the presentation. I hope that if you need time to go back and listen through the recording again, please feel free to do so. It will be posted later today. And again, just understand and appreciate that there can be some great things we can do when it comes to cloud, leveraging that password recipe, but of course with a little bit of salt added in for good measure. And with that, thank you. Oh, wait, there is a question here. So Brian, what about zero trust? Is this the same as passwordless that you referred to? Well, thanks for the question, Robert. Zero trust is a concept that there is no trust in the environment, whether it's internal or external. And so what that means to perhaps oversimplify, but to get an answer, every connection, every process, every transaction in an environment would leverage authentication and encryption. So it's not passwordless. It could be using a password. Zero trust just means that we don't trust blindly, we trust but verify. If a user was seated at a computer, we might ask them for their password again before they attempt a sensitive transaction. That's a concept of zero trust. They logged in once, but later on, we asked them for authentication again. So passwordless could be used to implement zero trust in a different way, but they're not intrinsically related. Does that, I hope that answers the question. It's kind of a tough one, but if not, I can circle back and try again. Grace asked a question. Is hashing passwords now more common than encryption? Well, I think, Grace, to follow up on your question, are you asking if hashing passwords is more common than using encryption for password storage? Is that what you mean by the question? Yes. Yes, hashing passwords is incredibly common for password storage today, but when it comes to legacy systems, you will still come across machines that do use reversible encryption, which is just shocking. Or to say it differently, it's the legacy systems in one's environment that are always the greatest concern. The functionality that we keep around because we have to, but we're no longer allowed to secure it, and that becomes the compromise point, resulting to the compromise of everything else. For your question, where I think you could go in the future is to determine, when you're looking at an authentication system, exactly how is the password hashed, what functions are they using, and then how securely are those hashes being stored. I think all of those things would be great for you to evaluate when you look at systems going forward. But a great question. Do we have any other questions? Feel free to ask. I'm happy to answer questions. I'll just give a few more seconds here. All right, with that, again, thanks so much, everyone. Truly appreciated it. If you have a chance to fill out the eval, please do so as well. Let us know. And I'm going to be doing more of these types of webcasts coming up, where we'll dive deeper into encryption and other aspects and keep tying it back to cloud, because cloud is going to be intrinsically so much more important going forward. On that point, I'll leave you with one final closing argument. There are many organizations that for many years have said they would never go to cloud. And in the last 9 months, they've made a jump to cloud, perhaps in some respects overnight. What we're going through right now is tough. It's tough for all of us. And one of the things that organizations had the ability to do to survive was to move to cloud. And after all of this is over and we go back to a more of a normal existence, so to speak, organizations are not going to come back from cloud. They're going to stay in cloud because they're going to understand the benefit of the survivability that cloud afforded and all the other benefits that go above and beyond. We should embrace cloud where we can. I know we can't use it for everything, but if we are enablers, if we understand that our job is to enable productivity in a more secure manner and not to get in the way of it, then we will be more successful as professionals overall. So with that, again, thank you so much, and we'll talk soon. I'll hand it back to Carol.
All right, well, thank you so much, Bryan, for your great presentation, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.